All right, everyone. In this video, we are going to introduce Gauss's divergence theorem, which is also sometimes just called the divergence theorem, that relates two different kinds of integrals to each other. Now, like most of our big theorems in Calc 3, there is a certain amount of setup that goes into it, and I will talk through that setup in just a moment. But first, I want to briefly jump to the bottom and say that this is going to be our punchline. So after we get the setup correct, the punchline is going to be that we can relate two integrals to be equal to each other. On the left, we're going to have a vector surface integral, and on the right, we're going to have a triple integral, so something that's integrated dx, dy, dz, or a change of variables, so d rho, d phi, d theta in spherical coordinates, for example. But this will be the payoff. So in certain circumstances, we will either be able to compute a certain triple integral, or we'll be able to compute a vector surface integral, depending on which one we might prefer. So that's where we're going. Let's talk through the setup of Gauss's divergence theorem. And there's a lot that we want to discuss. The key piece that we're going to be looking at is a certain solid region that we call D, as well as its boundary, which we'll just call the boundary of D, and we'll denote using this partial symbol, also the boundary symbol, and D. So D is going to be a bounded and solid region in three-dimensional space. Bounded just means it doesn't go off to infinity, so think like a sphere or a cube or a parallelepiped or a rectangular prism of some sort, but it's bounded, so it's not infinitely large. And it's solid in the sense that it's not a surface and not just a scattering of points. It's actually a 3D region sitting inside of three-dimensional space. So the two pictures that I'm going to draw one sphere. So here's my sphere. And then I'm going to draw one cylinder. And the cylinder and the sphere are both bounded and solid regions. So for these examples, we're imagining this is the fully filled in sphere and the fully filled in cylinder, not just the outer shell. And those are our Ds. So this is an example of a D, and this is another example. Now, let's talk about the boundary of D. The boundary of D should consist of finitely many piecewise smooth closed and oriented surfaces. So this is a 3D region. When I'm talking about its boundary, I'm talking about the two-dimensional surface that is like the skin of the region, the skin of the 3D region, or the outer crust of the 3D region. So the boundary of D, and it's going to be sort of hard to draw, but the boundary of D for our sphere is just going to be the outer part of the sphere, which is just the full sphere again. So the pictures look basically identical, but the key difference here is that the boundary of D is just the outer shell, while previously the boundary of D was the filled in sphere. Or I'm sorry, previously D was the filled in sphere. The boundary of D is just the shell. And in the case of the sphere, you can see that this is a single surface, and it is smooth, and it is closed. Closed just means that it doesn't have any that it how do I want to say that? Closed just means that it doesn't have any openings to it, like say an open interval would have an endpoint missing. There are no quote unquote missing pieces of this boundary of D. Now for the cylinder, it is not a single smooth surface because it has this upper edge and this lower edge, sort of like the outer rim of this can. But what it is it's three different surfaces. So we've got the flat disk up top, we've got this cylinder, right? And so I'm thinking of this as like an open cylinder. And then we've got this bottom disk. So we've got, in essence, the top, we've got the sides, and we've got the bottom. And we're unioning all three of these together. So we have three different boundary pieces here. So that's still finitely many. It's just three of them. Each individual piece is smooth. So the overall boundary is piecewise smooth. And every piece of this boundary is closed. So there are no missing like single points pulled out of it, for example. But yeah, so if we're thinking about the filled in cylinder, think of it as like a can of soup or something. Then it has three boundary pieces, three aluminum pieces, the piece on the top, the disc on the top, the open cylinder that consists of the side, and the single disc piece on the bottom. And so taken together, the union of those three comprises the entirety of this boundary. Now, each boundary piece is also supposed to be orientable, and we see that all of these are. So there's no Mobius bands or other weird non-orientable surfaces. And when we have an orientable surface, our choice of parameterization will give us an orientation. So when we pick an x of uv, we can calculate t sub u, t sub v, and tu cross tv. And tu cross tv will give us a normal vector, so it gives us a sense of orientation. Now we saw whenever we're orienting a surface, we have two possible normal vectors that point in our two different directions. So zooming in on the top piece here, the top of the cylinder, I could either have a normal vector that's pointing up, right? So like pointing, further up out of the can of soup, or I could have a normal vector that is pointing down into the can of soup. So two choices of normal vectors. And what we're going to do is we're going to orient each component of the boundary so that the normal vectors point away from the interior of the region. So they're pointing out into empty space. Now, this might mean at first pass that we create an x of uv and get the wrong normal vector, and we'll have to adjust by introducing a negative sign or getting a new parameterization or what have you. But we're going to orient it so all these normal vectors to the surface are pointing out of the surface. And then down here, for our multiple pieces, we'll just want to make sure that they're oriented consistently. So everything is pointing out of the surface. And that means for our top disk, it's pointing up into open space. And for our bottom disk, the normal vector is actually pointing down into open space. But we're going to orient each component this way. And we're sort of assuming implicitly in doing so, as we orient these, we're creating these x of uv parameterizations that can describe these surfaces. So this is our setup of the three-dimensional filled-in region D and all of its two-dimensional surfaces that comprise its outer shell, that comprise its boundary. Into all of this, let's take a vector field F that is just a vector field on R3, and at minimum, its domain includes all of the enclosed region D. So D, both the interior and the shell that is the boundary of D. Now, with that framework, these are the two integrals that are equivalent to each other. We have the the vector surface integral over the boundary of D. So that is our standard vector surface integral. And in a case where we have multiple boundary components, like in the cylinder case, we would have to calculate a vector surface integral for each of them and add them up. And so that is this object on the left, vector surface integral. And that will equal a triple integral over the entirety of d, I should actually make sure to include that in my formula. So this is the triple integral over the region d itself. So all three dimensions of it. And what we're integrating is the divergence of f. And as a reminder, divergence of f was equal to nabla dotted with f. So this was our del operator dotted with the vector field f. And that is the statement of Green's theorem. If we orient a closed, bounded, solid three-dimensional region and its boundary appropriately, we can set up these two integrals and they will actually give us the same thing. Now, let's calculate one example where we see that this is the case. So we'll save the conversation of why this theorem is true for another day. But let's see if we can, sorry. There we go. Let's see if we can calculate this for a given example. So we'll calculate the left-hand side, we'll calculate the right-hand side, and we'll see that the two are equal to each other. And in this example, we'll be looking at a unit sphere in three-dimensional space. And so the boundary of this will be the outer shell of that three-dimensional sphere. We have a given vector field, and so we'll compute the vector surface integral on the left, we'll compute the three-dimensional integral on the right, and we'll see that they are in fact equal. Now I'm actually going to start on the right because I think we'll see it's a little bit easier to compute. This is a triple integral over this sphere of the divergence of f dv. Now, because it's a sphere, I'm sort of anticipating spherical coordinates might be necessary here. But I'll actually point out that with a little clever trick, in this particular case, we won't have to use spherical coordinates. Because what happens when we actually compute the divergence of this vector field? Well, it's the x derivative of x plus the y derivative of y plus the z derivative of z. And so it's going to be a triple integral of just the function 1 plus 1 plus 1. So it's just a triple integral of the constant function 3. And so I'll point out we can pull this 3 out of the integral, and we're just integrating the function 1, which is always a slick way to calculate the appropriate size of the shape we're looking at. In this case, we're integrating volume, and so this will be 3 times the volume of d. Right, so that's a nice trick that we use when we're integrating just the constant function 1. This is great because we know that the volume of d, this is the volume of a unit sphere. Spheres have a volume formula that is 4/3 pi times the radius cubed. In this case, it's the unit sphere, so that's just 4/3 pi 1 cubed. And it's just thrice that. So 3 times 4/3 times pi times 1 cubed. And we're going to end up just getting 4 pi here as our answer. So if we had a more complicated integrand, if we weren't just integrating up 1, we would probably need to use spherical coordinates or some sort of clever coordinate system to compute this triple integral. But lucky for us, in this case, that is not so. So let's compare this to the vector surface integral on the left. The vector surface integral on the left requires a parameterization, x of uv. And so let's use the standard parameterization for a sphere, where our rho, our radius, is equal to 1. So this is going to be, I'll write out the full formula first, and then we'll fix it. So this is usually rho sine phi cos theta, rho sine phi sine theta, rho cos phi. All right. And then because we are letting rho equal 1 and phi and theta are u and v, let's let this become, so the 1 is implied there. This will be sine u cos v, sine u sine v, cos v. I'm sorry, cos u. I'm letting my u play the role of my phi here. Now, I'm not 100% sure that this is the best choice for u and v. It's possible I should have flipped them, so let my u be my theta instead. But flipping them will just result in the normal vector getting flipped down the road. So this is really our choice of orientation. It's possible I messed up, but we'll find out when we get there. So when we calculate our x of uv, we definitely need to calculate our tu and our tv, and then we'll do a tu cross tv. And so let's give that a go. Our tu is just the u derivative, so that will be cosine u cosine v. We'll get cosine u, sorry, cos u sine v, and then here a negative sine u. For our tv, we'll take the v derivative, so we'll get a negative sine u sine v. We'll get a sine u cos v, and then we'll get a 0. And so then when we go to calculate this normal vector, this tu cross tv, let's take a look. For our first component, we'll get 0 minus a negative sine u times cos v. So that'll be sine squared u cos v. And then for our next component, we will get a, so this is a negative, but then we're going to get a 0 minus a negative times a negative. So this is sine u times sine v. And I think my sign here is correct. The two negative signs canceled, and it was minus, but the middle term is always an extra negative, so minus a minus. So we get a positive sine squared u sine v. And then finally, this more challenging component, we're going to get cos u sine u times cos v squared minus a negative, so plus cos u sine v squared. And so we're going to get a cos squared plus sine squared of v there. And when the dust settles, it's just cos u sine u. All right, so let's just confirm sine squared u cos v, sine squared u sine v, cos u sine v, cos u sine u, apologies. All right. Great. Great. Um, and notice there's a sine u that's common in all of these. If you wanted to, you don't have to, but if you wanted to, I'll do it in a different color to highlight that it's perhaps optional. We could pull out a single sine of u from every single term, and notice what we get left over is sine u cos v, sine u sine v, cos u. And I just mentioned that because our initial parameterization was a sine u cos v, a sine u sine v, and a cos of u. So in fact, what we're getting in our normal vector is our original position vector times this extra sine of u, which is interesting. So we can verify by choosing a point. Let me see how I might want to do this. Let's choose a point. I'm going to say u equals pi over 2 so that that sine of u becomes a 1. Nice and easy. And let's say cosine of v equals, oh, cosine of v equals, I apologize. I just meant to say v equals, let's say v equals 0. So I'm going to look at this specific point. So maybe I should say at the point. I'll say note. At the point where u equals pi over 2, v equals 0, that's corresponding to, we get x of pi over 2, 0, which becomes a 1 times 1, sine of pi over 2 times cosine of 0. So we're going to get a 1, and then we're going to get a 0, and then we are going to get a 0. So this is at the point 1, 0, 0. And also notice the normal vector at pi over 2, 0 is sine of pi over 2, so 1, times the position vector, 1, 0, 0. So it's the exact same thing. So all I'm doing here is just verifying if I have my three-dimensional picture and I have my unit sphere. This is my unit sphere. Then at the point u equals pi over 2, v equals 0, I'm out here at the point 1, 0, 0, so sort of on the equator in the positive x direction. And my normal vector is the normal vector 1, 0, 0. So it is also pointing in the positive x direction. So I'm just verifying that this is, in fact, an outward pointing normal vector. And this is important because our goal in the statement of the theorem was to orient my surface to be pointed away from D. So we can verify that at least at this point, this is the case. The normal vector is pointing out of the surface. And because we just had a single boundary piece, right? The entire spherical shell is one boundary piece. This is the same for all of it. All right, cool, great, great, great. So now that we have this set up, let's actually compute the integral in question, the integral we were looking for. So the integral we were looking for, this is a double integral over S of f dot ds. So a vector surface integral, but it's really going to be an integral as u goes from 0 to 2 pi, and as u goes from 0 to pi, v goes from 0 to 2 pi. So I should just write these in to keep track of which is which. U is my current coordinate for phi. So it just goes from 0 to pi. And then the formula is for a vector surface integral, f of x of uv, dotted with the tu cross tv normal vector. So here's where I will need, let me see, I'll try to color code it. So I'm going to take my f from up top in blue, and I'm going to plug in my parameterization, my capital X. So I need the x coordinate, the y coordinate, and then the z coordinate. So that's exactly sine u cos v. And then the y coordinate, sine u sine v, and then cos u. Right? And then all of that is going to be dotted with my normal vector, which I won't be able to fit on this line, so I'll just write it underneath. And notice this is again, maybe trying to color code. So this will be my light green, my normal vector. I could use either of these. I guess I'll use the one down here. So that's sine of u as an extra scalar out front, and then sine u cos v, sine u sine v, cos u. All right, and then we're integrating all of that du dv. Phew, okay, so that's not looking too pretty. But let's go ahead and compute it. Our goal is to show in the end that this does in fact equal 4 pi. So let's see what we can accomplish here. First, let's just do this dot product. So we're going to have a sine of u floating out front. And then in parentheses, we have sine u cos v times sine u cos v. So that's sine squared u cos squared v plus, and then for our middle component, we're going to have a sine u sine v times sine u sine v. So that's sine squared u sine squared v plus, and then we're going to have a cos u times a cos u. So that's a cos squared of u. And then du dv. Let's simplify this before we start integrating. Notice in the first two terms, so I'll do this in red, in the first two terms, we have a sine squared of v plus cosine squared of v multiplied by the common factor of sine squared of u. So those two together will become just sine squared of u times cosine squared plus sine squared, which is just going to equal 1. So sine squared of u times 1. And of course, I don't need to include that 1. This original sine u is still floating out front of everything. Is that right? Yeah, of everything. I should put some big parentheses on here. But now this is just going to have that last plus cosine squared of u and the big parentheses, du dv. All right, and now we're cooking. The sine squared u plus cosine squared of u is also just going to equal 1. And so we are now ready to integrate as v goes from 0 to 2 pi, and as u goes from 0 to pi, the function sine of u times 1 du dv. And let's actually do this at long last. So the v is still going from 0 to 2 pi. When we integrate sine, we get minus cosine. And we're going to evaluate this for u as u goes from 0 to pi. And then we'll integrate dv. So the integral from 0 to 2 pi, we're going to get a negative cosine squared of pi. That's a negative 1. And then minus the negative cosine of 0. So that's minus a negative 1. So we just get 1 plus 1. And our final integral, notice there are no v's, our final integral will just be the integral from 0 to 2 pi of 2 dv. And so that's just 2 times 2 pi. And so that is just going to be 4 pi, which is exactly what we were hoping it would be and exactly what we saw from our other integral. All right. So this was an example of Green's theorem, at least to show the validity of Green's theorem. We set up an appropriate region D and an appropriate parameterization for its surface, the boundary of D. And we showed that the double integral, that is the scalar surface integral over the boundary, was equivalent to the divergence integral that was the triple integral. So the triple integral of the divergence over the interior of D. Clearly, the first way to compute this was a lot easier than the second. And so with Green's theorem, like with many of these theorems, we'll be trying to figure out which path forward is the easier path forward, and how we can use this theorem to simplify our lives rather than complicate it. So how can we turn complicated integrals into simpler integrals? But that's it for this video. Thanks so much for watching. See you next time.